This is the second part of the video on learning goal 1c, the atomic emission spectra and the Bohr model of hydrogen. In the previous video, part 1, we looked at success criteria A, using the Bohr model to explain what an atomic emission spectrum is and how it is produced. This video, we will look at the second two success criteria B and C. Now, some of this will be a good review of what you learned from part 1. Our first success criterion we'll look at for this video is success criterion B. Use the Bohr model to explain why atomic emission spectra are discontinuous, which will give us a very good review of how atomic emission spectra are produced, which we looked at in part 1. So the question is, why are these atomic emission spectra, why are they discontinuous spectra? Well, the most simple answer, and we can answer it in about 3 words, is this: quantized energy levels. Now remember, this idea of quantized energy means that the atoms, or the electrons in atoms, however you want to think about it, can only have certain specific amounts of energy. They cannot have any random amount of energy. The analogy that we have been using is that of using a ladder, where you can only stand on the rungs of a ladder. The electrons and atoms can only have energies of certain allowable amounts. Now, one way we can visualize this is to draw essentially an energy level diagram kind of looking like a ladder, where I have my ground state, or my first energy level, which I represent with this line here, and N equals 1. Recall that we use the notation N to represent energy levels. And then up here at the top, I have N equals infinity. This would represent when an electron has gained so much energy that it is no longer in the atom, that the electron has been ionized, and the electron is lost. It's no longer in the atom. So notice the higher we go on our diagram here, the more energy we have. Now we can add to this, we can add other energy levels, because there's more than just the ground state or the first level and the infinite energy level. We'll have N equals 2, N equals 3, N equals 4 on this diagram. Now I just stopped there just because I've run out of room. In reality, there'd be 5, 6, 7, etc. Now, one thing you might notice here is these energy levels are not equally spaced, and that is intentional, because one of the things that Bohr was able to show with his model of hydrogen, and we now know this applies to all elements, is that the higher up in energy we go, the closer in energy every energy level gets. So notice the third energy level is closer to 2 than 2 is to 1. Likewise, 4 is closer to 3 than 3 is to 2. If we were to draw the fifth energy level up here, it would be closer to N equals 4 than 4 is to 3. Every one of them gets closer and closer and closer. But just for the purposes of this diagram, I just put the 4 on there just so we can get them spaced out nicely. So part of this slide will be a good review of what we learned from the first part of this learning goal, as far as how these atomic emission spectra are produced. Along the way, we will also explain in great detail why we get these discontinuous spectra. So recall, electrons can only have certain amounts of energy. That's what these energy levels are representing. An electron could be here at N equals 1, it could be at N equals 2, it could be at N equals 3, but it cannot be anywhere in between. So atomic emission spectra are produced when an electron absorbs energy, and typically the electron would start in the ground state. And recall, that's the lowest energy state, so N equals 1, which I'm using this blue dot here to represent an electron. So if it absorbs energy, it's going to reach an excited state, meaning some other energy level, some higher energy level than the ground state. So the electron here, I'm showing it going to the third energy level. Which energy level it goes to just depends on how much energy it absorbs. In this case, the electron has absorbed enough energy to go from 1 to 3. So whatever the gap in this energy level is, now remember, each of these energy levels has an associated amount of energy. There's a specific amount of energy for each one. Now we're not going to worry about how much energy each energy level has. That's beyond the scope of our investigation and what we need to understand. But this gap in energy is the amount of energy that the atom would absorb to do this. If it only absorbed this much energy, the electron would go to the second level. If it absorbed this much energy from 1 to 4, it would go to the fourth energy level. So now the electron's here at this excited state, in this case the third energy level as we're showing. But as we know, because it's in an excited state, it's less stable. The electron and the atom are less stable, so the atom will emit energy. It's going to get rid of energy. Now when it does that, the electron has to move to a lower energy state. So it could go all the way back down to the ground state, and in fact that happens quite often, but it doesn't have to. In this case, I'm just going to show it going from the third energy level to the second. Now when it does that, when it goes down to a lower energy state, it has to get rid of that energy. Well, atoms do that by emitting photons, particles of light. So a photon gets given off. And this representation you see here, this squiggly arrow, is used to represent a photon in lots of these diagrams. The squiggly line representing an electromagnetic wave, or a photon. Now, notice I did make this a red line, and the reason I made it red is because if this is in fact hydrogen, and that's what the Bohr model is all about, this particular transition from n equals 3 to n equals 2, that will always give the red photon, because this gap in energy corresponds to the energy of a red photon. So speaking of that gap in energy, and here's why these spectra are discontinuous. The energy of the photon is the difference in the energy between the energy levels. So however much energy the third energy level has compared to the second energy level, that difference, that's how much energy the photon has. If we wanted to write an equation, it would be this. The energy of the photon would equal that difference, so E2, meaning the second energy level, minus E3, meaning the third energy level. Why 2 minus 3 instead of 3 minus 2? Well, we always want the final minus the initial, so it's ending at the second, it started at the third. That's why it's E2 minus E3. The equation itself is not that important to us. We just want to understand that it's the difference in energy that this photon has to have. Well, because of that, when this atom emits energy, every one of those emitted photons has to match the energy of our energy level diagram. So for example, we've said that this photon here is red, and not just any red photon, but a specific wavelength, frequency, energy, whatever you want to think about that. In hydrogen, the wavelength of that photon is about 656 nanometers. We don't get a photon with a wavelength of 658 nanometers or 652 nanometers because there isn't a gap anywhere that matches that. If we were to get one, say, that was slightly shorter wavelength, meaning slightly higher energy, we'd have to have another energy level just barely above the third one where this one is that would match that gap. But we don't have that. So let's continue to look specifically at hydrogen in order to understand all atomic emission spectra. The question I would like to address now is, why does hydrogen only emit 4 wavelengths of visible light? Well, I have another energy level diagram that's a bit more complex than the one we looked at before to help us explain this. So recall, hydrogen will only emit a red photon, a green or what looks more bluish green to us, a blue photon even though it looks pretty darn violet, and then a very violet photon bordering on ultraviolet, so it's hard for us to see. The reason that is those visible photons that are emitted match the gaps in hydrogen's energy level structure, which we see here in the middle. We have our red photon that gets emitted when we go from n equals 3 to 2. green from 4 to 2, blue from 5 to 2, violet from 6 to 2. We only get those colors and only those particular shades or wavelengths or frequencies or energies, however you want to think about it, because those energies match the gaps of those respective transitions. So why don't we get a slightly different shade of red, or why don't we get a yellow, or why don't we get an orange? Well, because there are no gaps anywhere in this energy level structure that matches that energy of that photon. If we wanted to get yellow or orange or any other color or any other shade. Now notice, even though we only see 4, there are all sorts of other emissions. So for example, all of these here, where we go from 2 to 1, 3 to 1, 4 to 1, those are all ultraviolet emissions, ultraviolet photons. We can't see them because they're not visible. Likewise, all of these here that go to 3, or if we had any that ended at 4 or 5, those are all infrared because those don't have enough energy. Now, one thing I should note here is this energy level diagram is not drawn to scale. With our ground state or first energy level here and the infinite level up here, if this was drawn to scale, this second energy level would actually be about 3/4 of the way up. It'd actually be about right here between 1 and infinity. The reason it's spaced out more is just so we can see more energy levels, so it's easier to read. So, in other words, what we're saying is if we had a slightly different energy level structure, or a completely different energy level structure, we would get different colors of light. We may get more visible photons, we may get fewer visible photons. It all just depends on how the energy level gaps correspond. But the whole idea is, going back to the initial question, why do we have discontinuous spectra, is because the energy levels only allow certain wavelengths or frequencies of light to be emitted. To finish up this discussion on why atomic emission spectra are discontinuous, I just wanted to show you some images of various other atomic emission spectra other than hydrogen, as that's been the focus of our discussion. While these emission spectra are much more complex than hydrogen's, with the only 4 visible photons or 4 visible wavelengths, the reasoning for these being discontinuous are identical. Every element has some sort of energy level structure where the electrons, and now we are talking plural because other than hydrogen, everything has more than one electron, where these electrons can only have certain allowable energies. Now, as you can see, because we have more electrons and because those energy level structures are more complex, and why that is not of our concern, the emission spectra are more complex. We get way more lines that are closer together, but they are still discontinuous. And every single one of the lines that we see in any one of these spectra, every single one of those energies matches a gap in the energy level structure of that element. And so this is why every element has a unique emission spectrum and why every one of them is discontinuous. So that concludes the discussion of why atomic emission spectra are discontinuous. The last success criterion for this learning goal, we want to be able to rank emissions and absorptions in the Bohr model by wavelength, frequency, and energy. So these next few slides are examples of how we do that. So let's take a look at what we mean by ranking emissions and absorptions in the Bohr model by wavelength, frequency, and energy. So the first thing that you'll want to do to answer these questions is to have in mind, and I would recommend drawing out a schematic for a Bohr energy level diagram. Now to do that, it's very simple. You need a ground state, so draw a line towards the bottom of your paper or whatever sheet you're working on for the ground state n equals 1. Draw a line quite a ways away from it to represent n equals infinity. You want as much separation as you can, just so you can have plenty of space to work with. From there, we know that the energy levels get closer together as you work your way up. So the second level, now if we were drawing this to scale, the second energy level would actually be about 3/4 of the way. Actually, it's exactly 3/4 of the way up from 1 to infinity. Now why that is not of our concern. And you don't have to draw it that way. You don't need to draw it to scale, but what you do need to do is as you draw them, draw each next energy level closer to the next one than it was to the previous. So 3 is going to be closer to 4 than it was to 2. 4 is closer to 5 than it was to 3. So as you go up, everyone gets closer and closer and closer. Now, I would recommend drawing up through 5, 6, maybe 7, depending on how much room you have. You don't need to draw any more than that. At least conceptually, you'll be able to understand what this energy level structure should look like. So just keep in mind the energy levels get closer together as you go. As long as you remember that, when you draw it out, you'll be fine. So for example, a simple question we might be asked, which transition emits a photon of greater energy? Is it when the atom goes from n equals 5 to n equals 4, or when it goes from n equals 5 to n equals 3? How I would highly recommend doing this is just drawing some arrows on your energy level diagram. So in the first one, we're going from 5 to 4. So I'm going to draw an arrow going from the 5th energy level, n equals 5, down to the 4th energy level, n equals 4. And I will compare that to what I have for n equals 5 to n equals 3. We can see this arrow here. Now remember what these lines are representing. These lines are representing the energy of each energy level. So the larger the gap, the greater the energy involved. So which transition emits a photon of the greater energy? Well, it would be the 5 to 3 transition because there's a bigger gap there. And the fact that we're going down from 5 to 3 means we are emitting a photon. So it would apply to both of those here because they're both going down. Let's look at another example. Which transition absorbs a photon of the longer wavelength? So n equals 1 to 2 or n equals 2 to 3. Now this time we're asked about absorbing, so we will be going up in energy, and it does so happen both these are going up. Now notice this time we're asked about longer wavelength, and we'll talk about that in just a second. Let's get our arrows drawn on our energy level diagram here. So the first one we have from 1 to 2. And the second option we have is from 2 to 3. Now again, get those arrows drawn on there so you can visualize it. Now you might be wondering, well, how would I know how to rank these, whereas before we had an energy level gap of 1 going from 5 to 4. Here we had going from 5 to 3, so it's a bigger gap. This one, they're both one energy level apart. 1 to 2 and 2 to 3 are both one energy level apart. But the key is, again, because of the way the energy levels are spaced. We know 1 to 2 is going to be a bigger gap in energy than 2 to 3 because they get closer as we go up. Now this question is asking us for the longer wavelength. So remember, longer wavelength would mean lower energy. So that's going to be the smaller gap. So in this case, it will be that 2 to 3 transition. So that would be your answer. Let's take a look at a slightly more complex example now of ranking these emissions and absorptions in the Bohr model. So let's say we had this question. Which transition in the Bohr hydrogen atom would emit a photon of the highest frequency? So we have two things going on here. We need to make sure we're emitting a photon, and we'll talk about how we deal with that in just a second. And we need to make sure we're thinking highest frequency. So we have these four possibilities: 5 to 4, 4 to 3, 3 to 2, 1 to 2. The first thing I would do is I would just draw those arrows on your energy level diagram. So we have going from 5 to 4, you can see that arrow here. We have 4 to 3, 3 to 2, and then 1 to 2. So the first thing we say is we need to make sure we're emitting a photon, getting rid of a photon. So we're emitting energy. Well, that means we have to be going down the energy level diagram. So that can eliminate option D, because that would be absorbing a photon, going up in energy. So it can't be letter D. Now the other thing, we're talking about highest frequency. Always relate that back to energy, because this is an energy level diagram. If we want highest frequency, then that is highest energy, because the greater the frequency of the light, the greater the energy of the light. So if we're talking greatest energy, again, we want the largest energy gap, not just the highest up on the diagram. So it's not this 5 to 4. We want the greatest energy gap, because remember, the photons that are emitted and absorbed, their energy is equal to the gap in the energy levels that the transition's happening between. So in this case, the answer is C, 3 to 2, because that's the largest gap in energy where we are emitting a photon. Again, it's not option D, because there we would be absorbing. Now that photon would have the greatest frequency of all of these, but that one's being absorbed, so it would not match our question. Let's take a look at one more example of using the Bohr model to rank emissions and absorptions. Now we're asked which transition in the Bohr hydrogen atom would absorb a photon of the longest wavelength, and you can see your options there. So again, get them drawn onto that energy level structure. So our options are n equals 5 to n equals 1, n equals 3 to 1, n equals 2 to 4, and n equals 1 to 3. Now, like before, we have two things to consider here. We need to make sure we are absorbing a photon, and we need to make sure we're picking the longest wavelength of those that get absorbed. So if we're asked about absorbing a photon, we have to be going up in energy, because when you absorb the photon, the energy of the atom goes up. So we can eliminate options A and B, because those would be emitting a photon or releasing a photon. So that leaves us with C and D. Now the second thing to consider is the longest wavelength. So ask yourself, is that the highest energy, the largest energy gap, or is that the smallest energy gap? So remember, longer wavelength means lower energy. And again, when we say lower energy, we don't mean lower on the energy level diagram. We mean the lowest or the smallest gap in energy, because the gap in the energy matches the energy of the photon. So in this case, the answer here is C, n equals 2 to 4, because that gap between 2 and 4 is smaller than the gap between 1 and 3. This takes us to the end of part 2 of the video on learning goal 1C in our completing the model of the atom unit. There are some check for understanding questions on your note sheet that you will want to answer, and we will pick this discussion up in class.